our website, and then here's our notes. Okay, so now let's shut me down here. There's my Voyager NASA work shirt. Now I'm gone. Okay, so real quick, we're going to put some other things up here. By the way, domain, I say input. What are you going to say? What's the opposite of input? What do you think? Output. So that's our new thing today, like good FOILers, good factors. Now it's input, output. You can graph anything that I'm going to show you this year through input, output. Chart of values turns into coordinates, and then the coordinates you can put on a coordinate plane. And I will tell you the idea of, and I know students are like, why do I have to graph and all this other stuff? Well, wax on, wax off. Anyone know the Karate Kid, the original? All right. You don't really have to know why, but I will tell you. I actually taught a stats class over the last 4 years, a couple years back. And that's where I really got the idea of what humans do. We try to look at patterns, and then the patterns that develop try to predict what's going to happen next. So a lot of things end up being patterns that can be described by equations, and then those equations help with those predictions. That's really what I would hope would be in your mind right now, so you understand that. And I think that's why science deals with a lot of graphs, and you do those kind of things. So try to have that in your mind throughout the year as to why we look at graphs, and then why we talk about domain and range. Domain is the input. A lot of times the input in a real world situation is time. Like over time, what do I see as the output of the data? Is it frozen? Let it go. Let it go. There we go. Is that what you're going to tell me? Thank you. And then in most equations, it is the x value. Okay? So I say most equations. We know we had some factoring questions where we had b squared, or a whole bunch of different variables all over the place. But when we get into graphing, we have an x-axis and a y-axis. The x-axis is the domain. The output is the range, which is the y. So do officially put that down. And I do realize I did not put my microphone in here, so my sound's going to be terrible for this movie. Really have bad sound on this situation. Okay, then go ahead and make this picture real quick so you understand the basis of why I would put a chart together. Basically, take these coordinates or these input outputs, they are a coordinate, and then you sketch those coordinates. And that's the Mickey Mouse basic idea of what mathematicians and scientists do. From data, they try to use an equation to predict what's going to happen next. That's what statistics is all about, actually. It's the oracle of today. It's statistics are all about predicting the future from past and current events. So awesome. A great show called Prediction by the Numbers from Nova. We watched that in stats, and it's like the first movie that we watched before I even start teaching why statistics. Now, I know many of you will be in calculus. That's great too. Again, calculus is a great class to describe what's going on in the world and many of the things that you do. May not be described as a word problem, wax on, wax off. It's just kind of like if you know this math, then this is useful math to describe the world kind of thing. So really hope you understand it in the beginning stages of your math career here. All right, so some things to write about this, and I am going to add to it. And don't get so crazy that you're writing every single box and all this paragraph over here, but I did want to give the book that you don't have, but I have access to, credit. So one thing over here, axis of symmetry, something to cover right here. X equals 0, that's a vertical line. And according to last hour, you did do lines a lot last year. You did equations of lines, y equals mx plus b, hopefully point slope form, standard form maybe. That's all stuff that, maybe reviewed this year, maybe not, I don't remember. But maybe next year for sure you got to know that stuff. But knowing x equals a constant, x equals 0 in this case, is a vertical line as an equation. And I made it dotted because it's not part of the equation or part of the line of parabola, but it's a thing that describes the parabola. And why it's called an axis of symmetry is it's symmetric. It's cut in half by that vertical line. So that's why it's called the line of symmetry. Hopefully you know what symmetry means. Did everyone scan in, by the way? All right, good. Making sure we're doing that appropriately. Okay, and then some other things I want to write over here. Like maybe to the right, I'm going to write domain and range. So I'll put that over here, domain. And we're going to really try to exercise this throughout the chapter. You know, that always, whenever we graph a parabola, no matter what the form, what's the domain and what's the range? So I know I told you domain is x, but when they ask what is the domain of a function, what can I plug in? That's what that really means. Well, for x, I can plug in anything. I can plug in positives, negatives, decimals, and square it. I can square any number. There's no limitations. First hour told me they remember what this looked like. All real numbers would be the domain, but actually what we write is negative infinity to infinity. And that's called interval notation. Raise your hand if you've seen that before. Right? And hopefully you remember that. Everything's going to be an interval notation instead of writing all real numbers. If you don't know, someone did have the courage to raise their hand, awesome. Like, wait, explain that. And just think of a number line. You know, number line 0 in the middle. I'm pointing in my class like I have a number line on my wall, but I don't. Negatives go left, positives go right. That number all the way down there is in a concept called negative infinity. All the way through 0 to their positive infinity. That's why that represents all real numbers. So if you never understood that, that's what it is. The range, though, is different. If we look at this, and I know you can't see my picture anymore, so you can't see my actions in class, I'll circle that right there. That's a gap. There are no y values that exist in that picture down there. The y values on the chart really start at 0, and I square a negative, they go up. Negative 2 squared is 4. Negative 3 squared is 9. And then 1, 4, 9. The y values, the smallest it seems they could be is 0. So that's what the range is. It's from 0 to infinity. Notice what I put on 0. Notice I put on 0 a bracket, because 0 is part of the range. It is one of the output values. So just asking, when they ask range, what are the y values possible for this function? And that's a little different than the domain. One other thing, interval, I should have put that over there. That's what I did the other hour. I put domain and range over here. Oh, well, I'm going to run off my sheet. Interval of increase. Sometimes it said intervals, but there's only one interval of increase. Now listen, the word increase is describing the y's and what they're doing. I want to make a point of this. This is really going to be a big deal tomorrow. Today you may not see it so much because how the answer comes out. So what it's saying is, and you don't get to see this in class, but I'm going to show an X finger, Y finger. So as I plug in, by the way, how do we read? What direction do we read? Which direction do we read that poster? From what to what? Left to right. So you read a graph the same way. That's not in all languages, but that's how math works, I guess. So when I input this X value, I have this Y, which is actually 16. When I input them in this order from left to right, what are these Y's doing right now? What are they doing in order? Increasing or decreasing? They're going down, so they're decreasing. But now, as I get to 0 and then I plug in 1, 2, 3, what are these Y values doing? Increasing. There's my interval of increase. But you name the X's to describe, because that's the X's you plug in order from left to right to create the increasing Y behavior. So those X's are from 0 to infinity. When I plug those X's in order from 0 to infinity, I get my increasing Y behavior. And then maybe I'll color that way, right? So remember this, because a lot of people name the Y's when this gets different. And you would get away with it on this one, but just to make sure. Go ahead. So, what do you have to write? Say that one more time. They say, what's the intervals of increase? They usually say that. Or where's the graph increasing? That's how the question's asked. Well, I'm going to that next. Okay. So then the next one is interval of decrease. In this case, there is only one. Again, the word decrease describes what is the y doing. I'm kind of short on colors here, so I'll probably use the same color for the x answer, but let's do the decrease in green. So we just said when we read left to right, that part is decreasing. But what I need to name is the x's that create that decreasing behavior, which I just kind of showed in yellow again. All right, now be careful. Just like what I said, I hope for range of that graph, 0 to infinity. You can't make it infinity to 0. You must name intervals from left to right on a number line. So this is when I plug in negative infinity for x to 0. Then I get a decreasing y behavior. The y's go down. Input, say it. So these are the inputs that create the decreasing outputs. All right, and that's the way we have to look at that so we don't make a mistake. All right, probably too much on that, but just to make sure. And I bet you did do this last year. Did you talk about these things last year with graphs? Yes, no? I think maybe. We'll make sure we really hammer that point down. And again, your notes are your own. If you think this is too basic, then don't write it. But then we're going to break down some other effects to a graph. Like, for instance, it's very easy to cover this input-output. And I don't like what the graph says for wider. We should never use that terminology because that's not true for all functions. But notice the difference between the green. The red is called the parent function, the very first one that we graphed, y equals x squared, and the blue. Let's start with the green, which says 2x squared. What we will call that is a stretch vertically. By a factor of 2, but I'll just say by 2. All right, so 2 is a factor. All right, so f of x equals 2x squared. 2 is a stretch of by a factor of 2, and it's very easy to see in this picture. So this original graph was 1, 1, all right, and we did graph that. That's the parent function. But what happens when you plug in 1 for x input? You do get 1 squared, which is 1, but then it's multiplied by 2, and you get an output of 2 now. It's stretched away from the x-axis. That's what stretch vertically means. All right? So just make sure you understand the terminology. And then the blue one, that is shrunk. Whenever it's less than 1, as far as a fraction is concerned, it's shrunk vertically, which means pulled towards. I got to move over a little bit. Okay, and then very simple to plug in there. You plug in 1, you get 1 squared, but then you multiply it by 0.5, and you end up being half as high as the green or the blue, the red graph. Sorry, trying to pull my colors out of my head. All right, so that's why it's called shrunk vertically. So today we're just talking about, hey, here's a parabola, input, output. That's why we get a parabola out of an x squared. And then here's some attributes that could happen after. And then tomorrow I'm going to show you a specific form of a quadratic. And then it's these changes. Maybe make a note to self. What happens with the blue graph? Very simple to analyze this input-output. First of all, they did sneak in this little example from the book, a 1.5x squared. So I did want to note to self, both of these are said to be vertically stretched by 1.5. But the blue one, very simple. I plug in 1 for x. 1 squared is 1, but then I multiply by negative 1.5. So now I got 1 comma negative 1.5. This parabola now goes down. So therefore, we will call that an x-axis reflection. Okay? Right? So whenever you have a negative on the front of a function, you'll call that an x-axis reflection. I'll say the word flip. I'll be lazy. I like the word flip over the x-axis. It's not that bad. Okay, so just make a note to self. Input, output can take care of that as well to explain how this happens. You still plug in 0 and get 0. So the blue graph and the red graph share that point. But then you can see why we get those other values. Okay, moving on. Can I go? What time do we get out of here? What does it say? 11:08. 11:08. Got 10 minutes. Won't take much. This is a nice introductory kind of thing. I kind of wanted to show this chart. Maybe put that chart down. You don't even need to see the equation. Hopefully you can understand that this is going to ask, it should ask domain and range. I'll really hit that tomorrow, but just make sure you understand the range is not all real numbers for parabolas. All right. We'll hit that when we have what's called vertex form, and things are going to move right, left, up, and down. It's really going to affect a lot of things that we're talking about today. But if you look at this chart, you have to understand this is going left to right. This is the way we go on a number line. -2, -1, 0. This is how we read a graph. What are these y values doing as I go left to right? Are they going up or down? 16, 4, 0, what did they just do? They went down. So that's a decreasing behavior. We should be able to read that in a chart. And then from here to here, I'm still reading left to right. But the reason I'm sectioning those off is now what are my y's doing as I go left to right? Now they're going up. So we should be able to see the increasing and decreasing behavior from a chart and see where the change is, see where the vertex is. You'll always see with a parabola a symmetry where the y values start repeating themselves. This always happens with a parabola. But in a chart, it's sometimes hard to see depending on how complicated the equation is. So just make sure you understand that as well as we move forward with this. So that's symmetry going on. So off to the right, I actually graphed this. I took those input outputs and I graphed them to see it further. And then I was able to see this actually decreases again, just like the original. Even though it's 4x squared, it just has a vertical stretch of 4. It still decreases from -infinity to 0. And then one thing I didn't say with you guys. Notice when I did range, I had a bracket on 0. Notice on increasing and decreasing behavior, it's always a parenthesis no matter what. And here's the idea, and I can make sense out of this for you. At 0, there's a change of direction. So a bracket includes an answer. So it's not increasing or decreasing at 0, actually. There's a change. So let's look at increasing. It's like saying right after 0, when I start plugging those into infinity, then the graph turns to increase. And that's kind of the philosophy with increasing and decreasing behaviors, and never, ever, ever using a bracket. You guys know what a bracket meant, right? That means include. I hope you understand that, but we'll hammer that as we go through. When you're naming increasing, decreasing, never a bracket. Never, 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 never. Our cat book, you may or may not see the cat book in the future, uses brackets, but I think philosophically that's not really correct. Then I don't think you have to write the next one down if you're trying to keep up with the notes. If you want to be a really stickler, like really write every single thing down kind of person, it's a chart again. Right? It gets better when we start moving stuff around, and then it's the vertex is not at 0, 0. Then looking at a chart and kind of analyzing. I think I have one more chart. Yeah, well, I'll kind of look at that one, I guess. You can kind of write this down just so you know certain sections of the homework. How do the values of each function affect its graph when compared to the graph of the quadratic parent? This is terminology, and I only pulled 2 of them out of here. So the one we just saw, 4x squared, that was actually the chart that we just saw. How is that compared to the parent function? By the way, the parent function will always be just the lonely very first thing that we graph, y equals x squared, input, output. Well, that 4, there's our terminology. The vertical stretch by 4. Skipping to 8, we have a negative. So it's reflected over the x-axis. If you put flipped, I wouldn't be mad. 0.4 is a vertical shrink. it's pulled towards the x-axis. That's what shrink means. I made a point of showing another function to my first hour, why it's stretch and shrink and not wider and skinnier. Because wider and skinnier does not work for all functions. You're going to find all functions have a parent function, and then these multipliers affect them the same way. You know, it doesn't matter if it's a square root, a cubed function, an absolute value function. Those are all different graphs, but they're all affected the same way. So that's why we use the same terminology. Okay, so stalling to give people time to write those two quick ones. 5. I'm not doing 6 and 7 because they're similar. All right, and then if you wanted to look at this, I just found this interesting. Say you didn't see this. Look at the y's here then, and then think about negatives. This is rough. A lot of students don't get this, that when I look at these y values to 0, negative 1.2 compared to negative 0.3. What's negative 1.2? Smaller or bigger than negative 0.3? It's smaller. It's like owing money. What would you rather owe, $2 or $1? How many people would pick $1? Raise your hand. See, $2 is worse. And I always think worse is smaller. I don't know why. You know, just thinking about the number line left of. But think of a number line. Negative 2 is left of negative 1, so it's smaller. So these are actually increasing because this is smaller than this, and negative 0.3 is smaller than 0. So these are going up as I go from left to right. Okay, I don't get that. Well, then good. Make a sketch of that. Then you'll get it. So make a quick sketch of negative 2, comma, negative 1.2. Negative 1, comma, negative 0.3. Then you'll see that that chart of value is actually going up to start off and then down after 0, 0. Okay, so giving a sketch will always work out there. And then good, I threw a domain and range back, and then we're pretty much not too bad here. So increasing, that's the yellow graph. And that's increasing from negative infinity to 0. I don't know if I made a point of this. If you switch these two, I'm marking you wrong. Because negative infinity is first on the number line far to the left. You always list this left to right on a number line. So negative infinity is left of 0. It must be negative infinity to 0. Decreasing from 0 to infinity. Remember, for domain, for specifically squared functions, it is all real numbers. But now notice this range. This range, none of these y's are covered. The graph doesn't exist up there. So none of those y values are on the chart. All right, so actually the range is, remember, you can't say 0 to negative infinity. You got to put it in number line order. Negative infinity to 0 are the y values that are covered. Here are the y values that are actually covered. These y values, the graph exists there. Those y values exist on the chart, but it must be 0, negative infinity to 0, not switched. Okay, those that switch, I do have to get you with the red pen on a test until you stop making a mistake. All right, and this is why you don't need me for this one. This is like a grade school example. Sure, it's a quadratic, but I guess it's trying to show the idea that quadratics can be used to, you know, real world geometry area questions. Don't we all know length times width equals area, right? So we know that x times x would equal the area here. A equals x squared, that's a quadratic. But anyway, then if x equals 13, you get 169 as the area. Okay, so a nice little introductory thing there. I don't think it was too bad. We'll move on with one of our forms for quadratics tomorrow and really work with it and really make sure we talk about domain range increasing and decreasing.